Hello, welcome back. This is Bob, and this is the fourth part of our four-part series, and this is taking a closer look at the current engineering system with a field trip. This field trip was conducted on March 17th, 2014, and I went on this field trip with Whitney, James, and Elizabeth with the Seminole Tribe, and Diane from FAU, a scientist, an ecologist at FAU. Well, the first thing we just drove by, and I thought it was worthwhile to put in this PowerPoint, was the G409 outflow, and that connects the tribe to its water right that comes through Confusion Corner. And here's the focus on close-in Google Earth view of Confusion Corner. Understandable how it got its name. And then the water is delivered from Confusion Corner to the Seminole Tribe. Well, our first official stop was at the S190, and here's a photograph of the S190. And the first question is how much water is stacking up on either side, on the headwater, tailwater side of the S190. And it turns out that water levels on the headwater side were at the top of their historic range because of the changed operational schedule that is experimentally being done since 2012. So there's the headwater, and here's just a hydrograph I already kind of had pulled together. Thought it would be worthwhile showing. The top graph shows rainfall, monthly rainfall levels collected at the S190 rain gauge, and then this shows the headwater tailwater differential. When we were out there was about a 4 to 5 foot headwater tailwater differential. Headwater was 4 to 5 feet higher than the tailwater, and we know that the headwater is just being caused by the gates of the S190 being closed, but what causes that tailwater elevation? And this I found really interesting, and the answer is it's the tailwater is a hydraulic backwater, an 18-mile long hydraulic backwater. And the way I determined this was I took this hydrologic snapshot for April 1st, 2014, and not to get bogged down in all the nomenclature here, but any white number is a stage above sea level collected on that day. So 15, here's the tailwater of the S190 is 10.97. The headwater is above 15 foot. And then just 18 miles downstream in the Mullet Slough the elevation is 10.84 feet above sea level. So you can see it's really a flat water surface all up this canal. Not that surprising during the dry season because there are no barriers in that canal. But it was really an eye-opener, and it would factor into any opportunities to release any of this water into the Big Cypress because there would have to be hydraulic controls sequentially run down the canal. Side point, but worthwhile, interesting to note. And then finally at the bottom of this hydrograph is an analysis of the headwater, the solid blue line, relative to its kind of ecological thresholds, which are stratified horizontally here by color coding. Here would be the deep drought, would be the red, and the real high water condition would be in purple zone. And see that dotted white line? That's the long-term median from 1997 to present, or going back 25 years. And you can see since the operational changes began that the headwater stage has been kept up higher than what would be the long-term average condition, normal condition. And if we then put this information into a calendar chart format, I call this a poor man's data dump. And again, this reads like a book from 1995 to the current year and across from January to December. When we're out in the field in March, water level was up in that purple zone. And you can see over the past 2 years, water's been almost exclusively up in the purple and blue zone, that higher elevation zone, with a little touchdown into the green zone at a few places. Compared to historically, you see places in the yellow zone and the red zone. The idea over the past 2 years, let's keep water as flush as possible in the north feeder and west feeder by closing that S190. So that new operation schedule has been successful at holding water back. The canals are flush, especially for the dry season. So it keeps the north and west feeder flush, and it also keeps groundwater levels up. If the canal's full, that keeps the groundwater levels in equilibrium as well. But ultimately, where does all that water go that's being stacked up? The answer is it flows through the S190. As we've discussed before, the fate of all those tailwater releases are 18 miles south. This canal was originally put in to bypass private property lands. Since 1996, when the land exchange occurred, land is in conservation status now, so there's no reason to bypass it. But nonetheless, we're in that status quo where we're sending that water downstream. None of it intermingles with the Big Cypress, and it discharges down in the Miccosukee Reservation, Water Conservation and Northwest Water Conservation Area 3. So how much water does the S190 release? Well, I went in. Currently, there's none. The gate was closed when we were there. But I went into the data set. The Corps of Engineers has a data set on that, and the USGS does as well. And I crunched the data. Not to go into the details here, but the back grayscale shows the historical stats with the white dotted line being the median. The blue line shows current conditions. And the average summer peak going through the S190 is around 300 CFS, and it's typically no flow at all between December and May. Again, if we do that poor man's data dump and look at the full period of record, you can see typically when it flows the highest is during the July through October months, during the wet season months. That's when we want to divert the water to send it into the natural areas. So that makes sense. And that's where we currently were. Currently are when I put this slide together at the end of May. Well, what is the annual volume going down the S190? I did that annual flow volume calculation in acre feet per year, and the 50% over that 20-year period of record, 50th percentile was around 125,000 acre feet, and here's where the other percentiles come up. The big flow year of note was the year of Hurricane Wilma, right? Almost 300,000 acre feet discharged through the S190, and then we had a couple drought years in 2007 and 2012. And particularly, the last 2 water years have been down, and that's partially a reflection of the changed operational schedule. If you're holding more water back, less water is getting through. Makes sense, right? So we can combine, here's a hydrograph, combines rainfall, headwater, tailwater, our headwater condition, and then discharge through the S190 in blue, and the across the west feeder in green. And I guess the take-home point is here, despite backing up all that water, we still have 300 CFS moving through the S190 during the wet season. So what are other options for sending that water south? Do we really just want to bypass all that conservation land? It's maintaining a status quo that was relevant decades ago and no longer makes sense. What are those possible release points? We've discussed this in previous slides. Releasing it across the L28 interceptor, using the siphons, sending directly south from the west feeder, possibly releasing it at the west weir. Well, let's explore those options. That was why we went out in the field. And what we did was we just drove along the southern levee of the west feeder from east to west. And then we went down to Kissimmee Billy Strand. And then we went back and we drove along the north side. So that's kind of a fast forward. But first we stopped at the first culvert that connects from the west feeder to the south. And again, the stage was a 15.5, so that's a really high stage. But even at that high stage, there seemed to be no propensity for the water to flow south. Definitely, there was no pressure or flow occurring. The second culvert to the south, same thing. It was just kind of a stagnant water body. We attribute that partly to the fact that there's nowhere for the water to flow. If you walk to the south, I don't know if it's disturbed land or just the way the landscape is there just downstream. It's not connected to a natural flowway per se. On our continuing driving west, we drove through the construction site of the second water resource siphon, and there's just some photos of the siphon. This is on the south side where the trench is. And then we went to the third of the 3 culverts, and again, that was the same situation. Despite the high stage, there was no indication of water flowing or wanting to flow south. Then we came, this was interesting, this is the the first water resource area that's actually already built along with the siphon. So here we are, the south levee of the west feeder, and here's the big trench for that siphon, the outfall trench. And the idea is water would flow from the water resource area under the siphon. This would rise up and then flow into the southern natural area. There's James. It's a couple hundred feet long, several hundred feet long for sure. And here the truck is on the downstream side, the south side of the trench, and this is the natural area. And it just so happened, it was great having Diane along. She knew where the old FAU monitoring station was. We had to walk past this pileated pecked log, and then we found the deep spot in the center of the strand where the old FAU well is. It's no longer collecting data, but there you can see the well. But we're still able to gather some important information. Diane had the elevations, and she's standing at 12.9 feet mean sea level. Remember, the stage in the canal is 15.5. So that means James standing at 14 feet above mean sea level, and I'm also standing where I took the photograph at about 14 feet above sea level. And the high water mark there, that means that high water mark is around 16 feet above sea level. But how often does water regularly flood up to that level? From what I've seen, not usually. So we're talking about your typical wet season, the wet season rising, let's say, 15, a little over 15 feet above sea level at its peak in this slope. So we continued to the west weir, and at the west weir, the water staff on the upstream side showed 17.5 feet above sea level, whereas remember in the S190 headwater pool 15.5. But when we took a closer look, there definitely wasn't a 2 feet differential between those two pools. It was closer to a half a foot or 8 inches. So why the difference? This was a little intriguing. Had to figure it out. Was it a surveying error? We see all that could happen, although you think not with the modern standard. Is the S190 headwater pool possibly not flat? So instead of from the S190 to the west weir being flat, that there's a little bit of a ramp? Could that be possible? Any other ideas? Well, it occurred to me after the fact that the answer was probably the work they were doing on the second siphon. That's probably backing up water. So, mystery solved. Then we went down to the second FAU well, and again, Diane was able to dead reckon to it. That was at 10 feet above sea level. That means Elizabeth standing at a 12.5 feet above sea level. That means that the main part of this flowway, which was dry when we were out there, is about 14 feet above sea level. So again, our elevation on our target flowway is around 14, just for argument's sake. So back up at the west weir, there's the west weir, and here's the diversion area structure for water resource area 1. So the water goes in two places. One, it goes to the S190, and the other, it goes to water resource area 1 through that pump station. But how much? So first, let's revisit how much water did we want to send south, right? Remember that? We did that calculation, and currently at 0, we don't want to do the Everglades overland flow accounting for 20 to 30% of the total hydrologic or water budget flowing in. We said it was more closer to the range of 5 or 10% for discussion purposes. And that should be 42.5, not 47.5. So the second is how much water do we have to spare? On a monthly basis going over the west weir, because arguably we're going to be taking water from the west that's going over the west weir and diverting it south. So here's a hydrograph of the west weir inflow. Again, the back grayscale is the historic stats, and the blue line is what's happened since 2012. And the take-home point here is that the average summer peak is around 150 CFS, and typically there's no flow from February to May. Now, if we superimpose our desired target flows, 5% would be this orange line, and the 10% would be the green line. And and then third, how much do we have to spare on a yearly basis? So if we look at the annual flow volume across the West Weir, that's what's shown here. On average, around, was it 47,000 acre-feet discharge across the West Weir. We have our flood years where there's greater than 70, and we have drought years when it's less than 20. And when we superimpose our overland flow numbers, if we want to get that 11,500 acre-feet per year diverted south, that's where that number would come up. We'd have that much water every year except these few drought years where we didn't really achieve that. So is there water available, and how much fractionally does it compare to those different elements of the system? Remember that the amount we're looking to release south, for discussion purposes, if we choose the 5% of direct rainfall, is equal to 25% of the water on an annual basis flowing over the West Weir, which is equal to 9% of the water flowing through the S190 on an annual basis, which is equivalent to about 42.5 cubic feet per second for a 4-month duration, which over an annual volume is around 11,500. So the answer is all above. But the question was, do we have enough to send that 11,500 to the south? And how much would it pull from the different parts of the existing system? So one has 5% historically been available. Again, we do this poor man data dump for the West Weir, discharge across to the West Weir from 1995 to 2014, January to December, and you can see anywhere that there's an orange dot, that means that we're at least flowing at that 5% rate. So, and that typically happens during 3 to 5 months of the summer season, at least. So that would reduce annual discharge through the S190 by 11,500 acre-feet. So fractionally, it's a pretty small portion of how much water goes through the S190. And how would we be getting that water there? And the current system is set up to have water from the water resource areas flow under the siphons into the natural area to the south. At least there was verbiage given to that. And currently, one water resource area and siphon are operational. And let's do the quick tour of that. What we did is we drove along the north side of the West Weir levee to stop at outfall 1A, to stop at the siphon, and to stop at outfall 1B. So here's 1A, and 1A discharges water out 1A. Here we're on the south side of the levee looking at where A1A discharges water into the west feeder. And it occurs it starts doing that when stage in water resource area 1 rises to 18 feet. We're going to skip by this slide really quick. That's just a little levee within a levee in water resource area 1. And then we stopped at the siphon. Here's a few photographs of the siphon, looking to the east, looking to the west, and to the north into water resource area 1, and then looking to the south. So the siphon, water has to overflow this wall and then go through the siphon underneath the West Weir and into the outfall out of the trench into the natural area. And this would occur at 19 feet above sea level. So water really has to rise up high. And then finally at the eastern end there's outfall out 1B, and 1B, from what I could gauge, looked like it overflowed at around 18.5 feet. And again, this is on the south bank. Out 1 and out B discharge right into the West Feeder Canal, whereas the siphon discharges under the canal and to the outfall on the other side. And here's what it looks like, all those elevations. So on the day we were out there, the stage in the West Weir was 15.5. I'm sorry, the stage in the S190 headwater was 15.5. The West Weir was 17.5. The overflow elevation in out 1A is 18. Out 1B is 18.5. And for the siphon, it's 19. And the slough floor, the flowway floor, is around 14 feet in the downstream area, and the siphon S1 tailwater trench is around, the lip of that is around 18 feet. So the issue here, in a nutshell, and I think we see it in this cross-sectional diagram, is, again, here's the west feeder canal, here's the south levee, here's the north levee, here's the elevation of the trench, really. So Out1A discharges right into the west feeder, and the siphon goes underneath. But it's perched so high, the inflow to the siphon, compared to Out1A, most water is going to be able to discharge through here before it reaches the elevation of the siphon. Our natural areas, the deepest holes, remember, that Diane was standing in was around 12 feet, and our natural flowway is estimated at 14 feet. And again, we'd assume the same thing on the other side of the canal. And the big issue is here, water level has to rise 3.5 feet deep, a depth in that natural flowway for water to lip over into Out1A. And then 4.5 feet, waters have to rise in that natural flowway before it lips over into the siphon. So what they've observed is that the siphons really only deliver water. It's not an environmental delivery of water. It doesn't occur on a weekly or seasonal basis, not even a weekly basis, not even a daily basis. They're observing it only happens for a few hours each year. So that's a problem in terms of sending water south with the siphons. The siphons aren't the cure-all or a guarantee to make those environmental deliveries to the south. So just looking at recent canal, the recent canal stage is 15.5. The record low was closer to 11. So you can see when water levels drop to 11, it just dries out the entire groundwater system around it. And the normal dry season low is around 13. And currently, if I'm not mistaken, that's here in June. That's what the water levels have dropped to. So there's lingering questions. Can the siphons be modified to increase the flow amount and duration instead of just being a flowing for a couple days during your peak stormwater event during the summer? Could it be designed to flow on a multi-week to monthly to seasonal basis? And how would that be achieved? Here's the siphon, the headwater siphons has to lip over at 19 feet above sea level, and the trench is at 18. So I think realistically we'd have to lower both the headwater and the tailwater side to get more water flowing from Water Resource Area 1 into the southern area. And here's a look at the headwater inflow side and the tailwater side. Not only would we have to lower potentially this wall, but we'd have to lower this embankment too to have a natural lower free flow of water from the trench to the natural area. The second is, can modifications be made to the west feeder to raise its stage? Under current conditions, that stage of 15.5 feet above sea level, which seemed to be at the high of the historic range, isn't enough to send water to the south. So to what degree could the west feeder be modified to raise its stage on its western end to send water south? Something to consider. And I just put this in for discussion purposes, so we had it. This shows from 2005 to 2014 the elevation of the S190 tailwater. The dark blue is the S190 headwater, and the red is the west weir. And you can see, if we superimpose, for argument's sake, and the dotted line indicating the estimated elevation of the slough at each of those points, what are the best places to, it shows the height of the water at those locations relative to the land surface. So gives us an idea on a starting point for looking at where are the best places to release water. And finally, number 3, to what degree can operational changes in the S190 help? And here's an overview of the S190. There's the S190 there. To what degree do operational changes help? As we've seen over the past 2 years, we've had the headwater at the top of its historic range, but it's still not high enough to send water to the free flow south from the west feeder. So I think the operations have to be looked at in tandem with some other engineering modifications as well. If we want to fold these environmental releases into the full solution. And here's a look at the S190 headwater and tailwater side. But I think the biggest question in front of us is, why are we maintaining the status quo? Why don't we take a trial and error approach and make a release? Because anything greater than 0 is an improvement than what we've had with our status quo, which is based on an assumption, the canal bypassing private property land, which is no longer the case anymore. We have all that land in conservation status. How do we add that restoration value to it as well? So in the short term, I would argue we need to continue pursuing a collaborative and experimental trial and error approach. Maybe the engineers say, hey, this is how much water we can spare. And the biologists say, hey, that's enough to start benefiting fox, squirrels, alligators, and help lessen drought severity during the spring. For the midterm, I would suggest 3 things: establishing 2 to 3 long-term continuous monitoring stations. This will put us on the path of being able to define those ecological targets and thresholds and target conditions that we're interested in. Number 2 is refine our assessment of the desirable and available environmental water release volumes. We did the back of the envelope calculation. That gives us something to build on. And third is to refine our engineering knowledge of all our release options. I think we're only scratching the surface there, and it's going to involve more than just looking at operations of the S190. We need to think of, how could we re-engineer the system to the benefit, to deliver those environmental benefits. And then for the long term, I think we want to get out of this maze. We want to figure out where the finish is. We want to define that finish and reach that finish. We have to define the finish before we can reach it. And I think that finish involves the biologists and the engineering perspectives coming together so that we have a working water system, and also achieve a restored swamp. Well, thank you for listening to this 4-part series. I hope it was helpful, and I hope it is a tool and a resource for our team to continue on the path of progress with. Thank you so much.